We're going to do some stoichiometry, some gas stoichiometry practice problems, so make sure you have a calculator and periodic table handy. Let's get started. So 33.9 liters of hydrogen is produced by this reaction. How many liters of oxygen would also be produced? So knowing that these two are both gases, we can see there the physical states. This is just going to be a one-step problem. So we're simply going to go from 33.9 liters of hydrogen to liters of oxygen. Go ahead and try the problem and see what you get. Okay, so as we talked about in class, as long as they're both gases, the coefficients, in this case 2 and 1, are not only molar ratios, but they're also volume ratios, because a mole of any gas occupies the same space. It doesn't matter the identity of the gas. So this reaction produces a 2-to-1 volume ratio of hydrogen to oxygen, so we get 17 liters. Okay, let's take a look at another one. The carbon dioxide from the combustion of 58 grams of methanol, which you can see right down there is CH3OH, is collected in a 100-liter tank. What's the pressure in the tank, assuming that CO2 is the only gas present when the temperature is 36.5 degrees Celsius? Okay, so let's go ahead and see if you can figure out a plan for this problem. Okay, so here's the way I wrote the plan. We're trying to go from grams of methanol, which we can then take to moles of methanol, and then to moles of CO2. This last step, I wrote it this way, but basically we're just saying if we can figure out the moles of CO2, we know the volume of the tank, we know the temperature of the tank, we should have everything that we need to find pressure. Okay? So let's go ahead and see if you can do grams of CH3OH to moles of CO2 right now. Okay, and there you have it. So we get 1.81 moles of CO2. I just used the periodic table to go from grams to moles of methanol, and then I used the balanced equation to go from moles of methanol to moles of CO2, which was just a 1-to-1 or 2-to-2 ratio. I get 1.81 moles of CO2. And if we look at our plan, now we need to take it to pressure. So I'm going to let you do that and try to figure it out based on the information given to you in the problem. Solve for P. I do want you to keep in mind that CO2 is the only gas present, so that means we don't have to worry about partial pressure due to water vapor or any of that. So give it a try. Sorry, I forgot to specify pressure unit. Let's find pressure in atmospheres. Okay, so there's my answer. I got 0.460 atmospheres. Kind of makes sense because we only have about, a little under 2 moles. 2 moles at standard temperature and pressure would occupy about 44.8 liters. Here we are higher temperature, so it makes sense that, a little higher temperature. But since we're in this big volume of 100 liters, it should make sense that our pressure would be very low. So we're occupying over double what 1 mole of gas would occupy. Over double what 2 moles of gas would occupy at standard temperature. So our pressure is a little bit low. It's about half of standard pressure. So let's go ahead and go to, and the other thing was, if you forgot to change your temperature to kelvins, that would obviously very, very, very much change your answer. You got to make sure you add 273 for your temperature. Okay, last question. So it says how many liters of chlorine gas would react with excess aluminum bromide to produce 40 grams of aluminum chloride at 0.988 atmospheres and 25 degrees Celsius. So what kind of reaction do we think this is? Okay, so it's going to be single replacement. And so if I have chlorine gas, so that's going to be Brinkelhoff, so it's diatomic, reacting with aluminum bromide. AlBr 3. That's ionic, so that's going to be a solid, unless it's aqueous, but it doesn't mention that it's dissolved in water. And then we're going to give, it's going to give us a single replacement, so we're going to get aluminum chloride, solid, and we're going to get bromine, which could be a gas or a liquid, but probably going to come out as a gas because of a little bit of the heat from the reaction. And then to balance, we're going to go least common multiple, so 2 and 3 for bromine, then 2 for aluminum, and 3 for chlorine. And now we have a balanced equation. Okay, so see if you can take it from there and write your plan, and then figure out your liters of chlorine gas. Okay, so there's the plan. We're trying to go from grams of AlCl3 to moles so that we can go to moles of Cl2 and then use the ideal gas law to go to liters. So see if you can get your final answer in liters of Cl2. Okay, so there's my final answer, 11 liters with 2 sig figs. Couple of quick reminders here. First of all, it didn't say anything about collecting it by water displacement, so we don't have to worry about subtracting a partial pressure or anything like that. Also, notice too, when I have these intermediate answers like 0.45 moles of Cl2, I want to keep usually one more sig fig than we're going to need in our final answer, which ordinarily would be at least 3 sig figs if I'm going to have 2 in my final answer, because we don't want to round too much here because it might affect our answer when we plug it in. But number one, I'm just leaving the number in my calculator. So when I get this answer, 0.45, and then I use it down here, I'm just leaving it in my calculator most of the time. Number two, this one was almost exactly 0.45. It was like 0.45001 or something. So it didn't matter, and it didn't affect my answer. So there you go. Volume equals 11 liters. Do a mental check, as best you can. About half a mole. We're not too far from standard temperature, and we're almost right on standard pressure. So it makes sense that this would be about half of a molar volume, which is 22.4.